Okay, welcome back. Welcome back to the course Geology and Soil Mechanics. So, in the last class, we have seen the sieve analysis, grain size distribution, and hydrometer analysis. So, and then we just started the consistency of clay with and Atterberg limits. So, basically, the consistency of clays is defined or is categorized by 4 states. First one is the liquid state, and then plastic state, and then semi solid state and solid state. So, there are 4 states by if you vary the water content or the moisture content of the soil or the clay soil, then you will be getting 4 different states, and those states are defined or associated with consistency of clays. Now, basically how you define these 4 states? First one is the liquid, as I told you, liquid state, plastic state, semi solid state and solid state. Now, if you come back to this figure, so basically you add water to a particular clay sample and you make a slurry. So, this is something like your liquid form if you get it. So, basically that comes under this zone. So, this is your liquid state. So, and then you reduce the water content from the sample, and then slowly from the liquid state the soil sample will be entering the plastic state. Okay. So, when basically you can deform the material. So, in the liquid state you do not have the option to deform it, rather it will flow, it will lose its strength. So, it will be a complete fluid kind of thing. When you reduce the water from this liquid state, basically slowly or gradually you will be entering the phase or the state which will be defined as plastic state. So, in the plastic state basically you can deform the soil. Suppose if you want to make a ball of the soil sample, or if you really want to do the clay modeling. So, basically you need to have the state which belongs to plastic state. Then from plastic state basically if you further reduce the water content or the moisture from the soil, then basically you will be entering the semi solid state. So, as you see, this plot is basically volume versus water content. So, as you reduce the water content basically you are also getting the reduction in volume. So, your volume is getting reduced, and so in the liquid state it will be having the maximum volume, and slowly it will be reducing to the plastic state and then semi solid state. So, then basically in the semi solid state once you reach at this point, then if you further reduce the water content, suppose in this direction you are reducing the water content, but you are not getting any change in volume, and that is known as solid state. So, in your solid state whatever, no matter whatever water content you are considering, so you will not be getting any volume change. However, once you cross the solid state, if you enter the semi solid state or the plastic state or the liquid state, basically your volume will be increasing gradually from semi solid to plastic and plastic to liquid by increasing the water content. So, this is by and large a clear picture about the consistency of clay. Now, when a fine grained soil is mixed with large quantity of water, the resulting suspension is in a liquid state, as just now I have told, and offers practically no resistance to flow. So, in the liquid state soil will not offer any resistance to flow. So, basically you will not be getting any kind of strength, it is a kind of soil water slurry. So, that is basically in the liquid state, or it will not be showing, or it will not be giving you any say strength. So, if you want to construct anything on top of the soil which is on top of the this clay soil, which is basically under liquid state, it will not carry or it will not give you any resistance or carry any load. So, that is basically your liquid state. Then the boundary water content between the liquid state and plastic state is called liquid limit. So, now we are defining different limits. So, the boundary water content between the liquid state and plastic state is called the liquid limit. Please try to understand, this is very important. So, based on these limits basically you can get the property of the clay soil. In the plastic state, the soil can be molded to different shapes without rupturing it due to its plasticity. As I told you, so if you are really interested in clay modeling, so you should have the soil or the clay under plastic state. If the water content is further reduced, the clay sample changes from plastic state to the semi-solid state at a boundary water content which is called as plastic limit. So, this is the boundary of your plastic state and the semi-solid state. So, that means from the plastic limit to liquid limit, the soil will be exhibiting the plasticity or the plastic state. Up to the semi-solid state, the soil remains fully saturated, and any reduction in the volume of water will result in an almost equal reduction in the volume of the soil mass. A further reduction in water content, however, brings about a state when, with a decrease in moisture, the volume of the soil mass does not decrease any further, but remains the same. The sample changes from the semi-solid to solid state. As I told you, in the solid state, basically whatever moisture content or whatever water content you consider, or if you reduce the water content, if you increase the water content in the solid state, basically you will not be getting or observing any volume change in the soil matrix. The boundary water content between semi-solid and solid state is called as shrinkage limit. So, this is the boundary between semi-solid and solid state. So, that means from between shrinkage limit and plastic limit, the soil will be behaving as a semi-solid state. Now, liquid limit can be defined. It is generally represented as WL and it is defined as the water content at which a soil is practically in a liquid state, but has infinitesimally resistance against flow. So, basically you do not have any resistance to the flow. Liquid limit is defined as the water content at which a groove cut in a pad. So, this is again related to your laboratory experiment. So, basically you have some standard liquid limit device, and there basically you have some small bowl, and inside that you will be putting some soil by mixing with different moisture content, and then you will be cutting the groove with a standard say cutter, and then you will give the blows. That means that whole bowl will be going up and falling down, and then at a then slowly that whatever groove you have cut, that groove will be touching each other, and then based on that we can plot the flow curve, and then that flow curve we can determine the liquid limit. So, this is the laboratory experiment device. Anyway, so the liquid limit is defined as the water content at which a groove cut in a pad of soil by a grooving tool of standard dimensions will flow together for a distance of 13 millimeter under the impact of 25 blows in a standard liquid limit device. So, this is basically your laboratory experiment device. Now, basically what you get here. So, this is your flow curve. So, you take some soil sample, you mix or if you mix different say amount of water, and that means you are varying water content, and then basically you are putting that sample in the standard liquid limit device, and then you cut the groove with the standard tool, and then you give the blows, and then you observe that the flow of the groove, that means the groove is touching each other. So, basically suppose I am applying some water content W1, okay, and I am giving the blows, and then at this number of blows say I am getting the groove is touching each other or the flowing of the groove. So, that means I am getting this point. Similarly, I am varying again the water content of the same sample like this. I am getting another point, that is this is the number of blows, say 40 number of blows, which will be causing the groove to come closer, then I am getting another point like this. So, I will be getting in that way, if I do the test for different water content, I will be getting different number of blows to get the group which is touching each other, and ultimately I will be getting this flow curve. So, this is my flow curve. Now, what I do at 25 number of blows, say 25 number of blows will be coming somewhere else, I will be drawing one vertical line and I will be getting the water content. So, this is my liquid limit. So, in that way basically we do in the laboratory. So, from the laboratory test we can determine the liquid limit by this method. So, this is my liquid limit. So, plastic limit, that is WP, is defined as the water content at which a soil would just begin to crumble when rolled into a thread of approximately 3 millimeter diameter. So, basically you in this plastic limit you take the sample out, generally we do this thing from the liquid limit device we take the soil sample, because as we know the plastic limit is always lesser than your liquid limit. So, whatever water content is there in the liquid limit test, so that material if we take out and slowly or gradually if the water is getting out, and we will be getting the plastic limit. So, what we do here, we take the soil sample, we roll it in 3 millimeter thread and 3 millimeter diameter say soil sample, and we roll it. So, when the soil is just begin to crumble, so that at that time whatever moisture content is there, so that is my plastic limit. Now, sinkage limit is the maximum water content at which a decrease in water content does not cause any decrease in the volume of soil mass. So, this is the maximum water content at which a decrease in water content. So, if you further decrease the water content, your volume of soil will not change. Now, based on that we will be defining this index, that is very important index, that is plasticity index. Based on that basically you will be classifying the soil clay particularly. Later on we will be seeing from the classification system. So, plasticity index is defined by the difference between liquid limit and plastic limit. IP is the range of water content over which a soil exhibits plasticity. So, basically this is the range of water content. So, if I say WL minus WP, as I told you, this is the difference between liquid limit and plastic limit. Within that range basically your soil will exhibit the plasticity, right, the soil is in plastic state. IP indicates the degree of plasticity of a soil. Greater the IP, greater is the plasticity of soil. So, if any soil particularly if you consider, if you observe higher plasticity index, then that means that soil will exhibit higher plasticity. Now, this is a table which will give you some indication or the idea that how the soil consistency is dependent on plasticity index. So, if IP is 0, the soil description or soil is described as non-plastic soil. If it is less than 7, then low plastic soil. If it is 7 to 17 within that range, then it is medium plastic, and then if it is greater than 17, then it is highly plastic soil. So, based on that we can categorize whether it is non-plastic soil or low plastic soil or medium plastic or highly plastic. Now, if you take or some sandy particle or a sandy soil, and then if you try to find out the plasticity index, you will observe that IP is very close to 0. So, that is non-plastic. So, sand is completely non-plastic, and that is why you cannot model the sand modeling. Now, coming to the relative density, it is generally expressed as dr or rd in different books. Now, this relative density is nothing but this is the property of the sandy soil. So, earlier we have seen the consistency of clay, that is Atterberg limits. So, they are basically associated with the clay soil, that is a fine grained soil, whereas to quantify or to get some idea whether the sand is very loose or state or the sand is very dense state. So, that kind of idea if we want to get it, then we need to calculate the relative density. So, relative density is purely associated with this sandy soil or the coarse grained soil. So, dr or rd is equal to E max minus E natural by E max minus E mean into 100%. So, it is generally expressed in percentage. Now, what are these E max and E natural? So, E max is the void ratio in its loosest state. That means dr is defined as the ratio of the difference between the void ratio of a cohesionless soil in the loosest state, the void ratio of the cohesionless soil in the loosest state, that means Emax, and the void ratio in its natural state. So, whatever soil sample you are considering, that soil is having some natural void ratio, that is E natural, okay. And Emax is, if you consider the soil sample in its loosest state, that will give you the Emax, which is the maximum void ratio the soil sample can have. 2. The difference between its void ratio in its loosest and densest state. So, E mean is nothing but the minimum void ratio the soil sample can have, and that is at the densest state. So, that will give me the relative density, and it will give me the idea that based on the relative density I can say whether it is the dense soil or medium dense soil or the loose soil or the something like that. The degree of denseness or looseness of natural deposits of coarse grained soil can be measured by relative density. So, this table will give you the idea between your relative density and the classification of soil, like if dr is less than 15%, then it is very loose soil. So, as dr increases, it goes to the densified soil. So, 15 to 35 it is loose, 35 to 65 it is medium, 65 to 85 it is dense, and if it is greater than 85%, then it is very dense soil. Okay. So, now we will be taking one problem, whatever we have seen or whatever we have defined, some simple definitions we have come across. So, based on that we will be taking the first problem. So, the problem says that undisturbed sample of saturated clay has a volume of 16.5 cc and weighs 35.1 gram, and on oven drying the weight of the sample reduces to 29.5 gram. Determine the void ratio, moisture content, dry density and the specific gravity of solids. So, as you have seen different definitions, and these are the properties available with you. Based on that you need to calculate or need to determine these parameters. So, let us solve this problem, so that you will be getting some idea that how to crack this kind of problem and how to get different properties of the soil. We will be solving this problem by two methods. First, the method 1. So, what are the things are given? You have volume, total volume, then total weight, and then you have the dry weight of the sample or the weight of the dry sample, and then degree of saturation, that is S. So, these things already we have defined and already we have seen in our previous lectures. And what are the things are required to determine? Void ratio E, water content W, dry unit weight or the dry density whatever, and specific gravity. So, these 4 things you need to calculate. If you know these 4 things, how to calculate or how to obtain these 4. So, let us see step by step. So, you will understand the steps. Now, weight of the saturated sample is given as 35.1 gram. Okay. Similarly, weight of the dry sample is given by WD is equal to 29.5 gram. So, weight of water evaporated that is nothing but WW is given by, very simple, that is the total weight minus the weight of the dry sample. So, that will give me the weight of water which was present in the sample. So, that is nothing but 5.6 gram. Okay. Therefore, because the soil is saturated, so I will be getting the bulk unit weight which is nothing but your saturated unit weight, which is nothing but this, very simple, as we have seen already. So, these are the definitions already we have covered in our previous lectures. So, gamma sat is equal to W by V, which will be 35.1 by 16.5. So, V is given and it is coming as 2.13. So, I am doing all the things in CGS units. Anyway, so this is gamma sat. So, 2.13 gram per cc, which you have just got it. So, once you have got gamma sat, then you can calculate gamma D. Now, what will be the expression for gamma D? Gamma D is nothing but the dry unit weight of the soil or the dry density of the soil. So, unit weight and density basically the difference with respect to the g, small g, okay, acceleration due to gravity. Anyway, so the how to obtain gamma D? Gamma D is nothing but the weight of the dry sample WD by the total volume, which is nothing but 29.5 by 16.5 is equal to 1.79 gram per cc. So, we have got it just now. So, this was our objective. So, we have got gamma D, but gamma sat. So, these are the things I am not going in detailed derivation and all. You can find out that thing from the basic definitions. G plus E by 1 plus E into gamma W, where Gs is the specific gravity of the soil solids, E is the void ratio and gamma W is the unit weight of the water. So, from this expression can be derived. So, by from the basic definition. So, that derivation I am not going in much detail. So, that you can get from any other textbook or from the basic definitions whatever we have covered, from that you can calculate or you can determine that. So, the gamma saturated is given by this. So, what are the things you know from this? So, from this expression or from this thing you can write down Gs is equal to 1.13 E plus 2.13, which is equation 1. Again, gamma D is equal to, again this can be derived. Again, I am not showing you the complete derivation, that you can see or you can find out from your simple definitions whatever we have covered. So, gamma D can be expressed in terms of this Gs into gamma W by 1 plus E. Now, if you put all the values, so gamma D already we have calculated 1.79 is equal to Gs into 1 by 1 plus E, and from this we can calculate Gs 1.79 E plus 1.79, say equation 2. Now, by solving these two equations, equation 1 and equation 2, we can find out E is equal to 0.51. So, your void ratio is 51%. Okay. So, you have got E. Now, from equation 1 or equation 2, whatever you feel better, you can calculate GS is equal to 2.71. So, we have got out of 4 parameters, unknown parameters, we have got gamma D, E and GS. Now, water content is left out. So, we can calculate water content. So, water content W is given by AC by GS. Now, what is the value of S? That is the degree of saturation in this particular problem, completely saturated soil. So, that means S is 1. So, 1 and your void ratio is 0.51 divided by 2.71, it is coming as 189, that is 18.9%. So, you have got all the 4 unknown parameters by knowing those 4 parameters whatever we started with. Now, this is by method 1. So, we have calculated because these equations we have put. Now, in the next lecture we will see by solving this same problem, okay, by using some different method, method 2, which is based on your phase system, whatever phase system we have understood or we have seen in the last lecture. Thank you very much.